Hi everyone. By this time in the course, you would have gotten through alkene reactions, and possibly, depending on your professor, you'll be starting alkyne reactions, reactions of the carbon-carbon triple bond. The lab also is going to be tracking this learning of reactions because now in lab, you'll start to get away from learning new techniques and now learning how to run reactions and how to deal with things like percent yield. In this video, we're going to talk about limiting reagent equivalence, which is that EQ. And I want to use an example, an alkyne halogenation, to show you how to make a lab stoichiometry table. The reaction that we're going to be looking at is the alkyne halogenation. And you may or may not have gotten to this in class just yet, but you should be familiar with this because it uses the pi bond. An alkyne has two pi bonds, and we are going to add Br2 and create butane with 4 bromines. So hopefully you can tell that we need 2 equivalents or 2 Br2 molecules to react with every 1 molecule of, the name of this is 2-butyne. And essentially you're adding Br to each pi bond. And again, the triple bond has 2 pi bonds. Before we get too far with this reaction and onto the stoichiometry table, let me show you. I have a video pulled up. Let me find it. Oh, here it is. Bromine is a brown, thick liquid, and I don't have the sound here, but this video is called "Don't Ever Pour Bromine on an iPhone 6S." So look how thick that liquid is, that vapor, but it's a liquid, and yes, we are going to be using this in lab, but it's very caustic. You don't want to get this obviously in your eye, definitely not your skin as well. Okay, so let me go back to this reaction. We're going to call these two things, these two molecules, starting material. Or sometimes they're called reagents or reactants. Usually there's going to be a solvent, and I like to put the solvent underneath the arrow, and this is chloroform, and we'll call this obviously the solvent. And this is the product. In organic chemistry, normally you don't put coefficients next to your compounds, but remember how I said that we need 2 bromine molecules? Sometimes instead of putting 2 for the coefficient, your professor or the textbook may say 2 EQ, 2 equivalents, and you're going to assume that there's this 1 equivalent. Okay. Now, in this video, it's going to be a little bit different because I'm going to jump back and forth between some notes and what I expect my students to put in their lab notebook. All right, so you will be pausing this video a bit as we go through certain sections in the lab notebook. Okay, so here's how I usually start my lab notebook. And yes, for this particular lab, I'm going to call it simply lab stoichiometry table for alkyne halogenation. And here's a date and a page number. Here's the reaction, okay? And there are a couple things I want to point out about the way I draw the reaction. I don't want to keep calling this 2-butyne. I don't want to keep writing that. So I'm going to give it a notation. I'm going to give it a 1 with a squiggly line underneath. Usually in an article, that 1 is going to be in bold, but I don't, it's hard to sometimes differentiate between bold and unbold when you're writing by hand. So just put a little squiggly line. BR2 we'll just call BR2. Okay, so there's no need to put a shorthand for that. And this is the product. Okay. Now, this is all theoretical, but pretend that you have an article and it tells you to use, oh, here we go, 1.15 milliliters of 1.72 milliliters of Br2, bromine. And this is what I want on the lab notebook. Okay, we call this a pre-lab entry. How do you prepare your notebook before you actually do the reaction? Okay, and then there are some numbers that I want associated with each of these to figure out moles, right? You need the molar mass or the molecular weight, MW and molecular weight, and I already wrote those here, so you could copy those into your notebook. The other thing is, let's see. Oh, since it's a liquid and I need to get moles, do you see how I need the density? Right, I have a volume, but this number does me no good figuring out moles because it's in grams per mole. So these are the volumes for each of those two liquids. It's kind of rare. Most reactions have maybe one solid reactant and one liquid reactant, or two solid reactants dissolved in the solvent. The last thing that I would like on the chemical reaction in a lab notebook is the theoretical amount in grams. And we're going to figure that out in just a bit. It's very good to have at the very beginning, have an idea of how much you should get at the end. Is it going to be 5 grams, which is about a nickel, or is it going to be 20 grams, like a palm full of sand? You want to have a good idea of how much you expect to get. So, you could troubleshoot along the reaction, along your purification, and you have a good idea when you get to the end that, oh, did this reaction work? Or do I have a lot of impurities, etc. So I insist my students to put the theoretical amount, which they have to calculate based on the amounts. Okay. Now, next is the purpose. And this is not a lab that I'm literally going to do because this is a theoretical lab that I want to use to show you how to write again, the stoichiometry table. The stoichiometry table. Okay. But normally you would say to synthesize X via some technique, whether that be there's a technique called reflux. There's lab grade microwaves, so there is microwave syntheses right now. So there's a bunch of different techniques. Just give me something in a real lab. How are you running this reaction? What's so special about it? Is it air-free? Is it solventless, etc.? Okay, but for now, just put a line. And then we have the source. Okay. Now, if this is the first time you're writing up a reaction in your lab notebook, you're going to need to put limiting reagent calculations. And you've done this in general chemistry. I'm going to show you how to do this again here for this organic chemical reaction. I want us to get the theoretical amount, pretending that 1 is the limiting reagent. And then we're going to do it again, pretending that Br2 is the limiting reagent. So we're going to do 2 sets of calculations. This is what I do want to see in the notebook. This is not for scratch paper. Okay. All right. We're going to use dimensional analysis to try to get grams of the product. So for 2-butine, we are using 1.15 milliliters, and I do want to put the compound 1. Okay. That's actually for me very important because we're going to have to cancel that out and get grams of product. We have a density, and the density is, let me just move this pad away. We have a density of 0.69 grams per milliliter. Okay, so that's good. We could cancel out milliliters. 0.69 grams per milliliter. Okay? And then we have the molar mass. The molar mass is, you might have this already in your notebook, 54.09 grams per mole. So that's grams per mole, but do you see how I need grams on the bottom and moles on the top to cancel out the grams? So there's 1 mole, and again, it's 54.09. So here's the important one. Okay, well, they're all important, but here's a critical conversion that I need to see. This is what I'm looking for, because it depends on your ability to interpret how many of these molecules you need to make the product. Do you see how we have 4 carbons here and we have 4 carbons in the product? So that's a good indication that you have 1 part reactant turning into 1 part product. It's a 1-to-1 ratio. So yeah, we are going to have 1 over 1, but why is that important? Because you're literally going to say 1 mole of product per 1 mole of 1. Do you see how by doing this, and don't circle this in your notebook, but I want to circle it to emphasize it, by having this conversion, we are now able to cancel out 1, okay, the compound 1, and have left behind product. Okay. Why don't we cancel out a couple other things? Milliliters, grams, and even moles. Okay. So if we do this calculation now, we'll have moles of product. So that's good, but I'm asking my students to put the grams because it's hard to tell if you have a pile of powder how many moles that is. But with practice and with experience, you'll know approximately how many grams that is. You'll know whether it's 1 gram or 50 grams. You'll have that intuition. So times, and so we're going to take the molecular weight. And if you run out of space, which I think I am, just start a new line, and I or your grader should be able to follow. So it's grams per mole. We don't have to put grams of product per mole of product because we have the product already here. You just have to cancel the moles. And do you see what we're left with? We're left with grams of product. Okay. And that is our first calculation to figure out how many grams of product will we get if all 1.15 milliliters of 1 are converted into product. For these calculations, I like to press enter after every operation. 1.15 times 0.69 equals. Okay, next, divided by 54.09. Divided by 54.09 equals. Times 1, okay, and then times 373.71 equals. So that's grams, 5.48 grams. And it's grams of product. Okay. If all of 1 is converted into the product, we should expect 5.48 grams of product. Let's do BR2 and see how many grams of product theoretically we would get for that. BR2, at the top of the page, under your reaction, it says that we are using 1.72 milliliters of BR2, that brown, thick liquid that creates a lot of fumes. Oh, shoot. Why did I show you that video? Okay, I showed you that video because, see, BR2 starts out as a dark reddish liquid. Dark reddish liquid. If you're able to consume all of it or most of it, then you'll have no more BR2 and the solution will start to get lighter or decolorize. So as Br2 reacts, solution decolorizes. I want people to understand that concept. And you could tell if it starts to get lighter, that's a good indication that you have a pi bond. That you are reacting. Okay, and when all the pi bonds are reacted, you have an alkane, right? This can I name it? I haven't named it yet. I'll name it in just a bit. I'll name it right now. This is 2, 2. I must have named it somewhere, right? Oh yeah, right here. 2,2,3,3 tetrabromo butane. Okay, but this is a, a reaction that decolorizes with time. All right, and again, it's a good indication that you have a pi bond. It's a good test. Anyway, can you try to do the calculations? And don't forget this is the mole ratio. Okay, here, remember, by inspection, right? You should be confident and have an intuition that, oh, I have 4 carbons and my product has 4 carbons, but now it has 4 bromines. So I added Br2 twice. So what is the conversion factor you need? 1 product or 1 mole of product over 2 moles, right? 2 moles of bromine, because you need a total of 4 Br atoms. You want to pause the video and give it a shot and do the same calculations and see whether we get more product or less product by doing this type of dimensional analysis. Go ahead and pause the video, and when you come back, I will have this. I'll show you how I would do it. Okay. I think when you're first learning this, it's important that you literally cross out the units that also cancel. Okay. But I have, what is it, 3.12 grams per milliliter density. And then you take the inverse, right, of the molecular weight. Grams. Okay. At this point, we have moles of bromine, and literally, you can see that milliliters cancel out, grams cancel out, and we have moles of bromine, Br2. But we really need grams of product. So this is where when in doubt, draw your horizontal line and figure out, what do I need to cancel? I need to cancel out bromine. And sure, you could put molecular bromine, but I think it's just easier to say mole of bromine. But how many moles of bromine do you need per product? So that's 2 moles of Br2 to make 1 mole of product. See, that's the key conversion. That's the mole ratio. And again, I'm going to have to go to another line. And the product molar mass is 373.71 grams per mole equals. Because look what's going to cancel out now. The moles cancel out. The Br2 canceled out. And a mole again, mole here and a mole down here. We have grams left over, a product left over. Okay. Let's see how many grams of product we get if we consider all of the bromine being consumed and incorporated into the product molecule. Okay, again, 1.72 times 3.12, and I like to press enter after each operation. Okay, so I have that number saved. Divided by 159.81 equals, divided by 2, not times by 2. Divided by 2. By Doing this by doing this dimensional analysis, you don't have to memorize, well, I don't know, we have a 2-to-1 ratio. Do I divide by 2? Do I multiply by 2? Just make sure you cancel out the right compound. You want bromine on the bottom, right? Because you want to cancel out the bromine on the top. You want products on the top because eventually you want grams of product. So that should help clarify or keep straight, oh, in this case, I have to divide by 2. Now, it could totally be different if you need, if one molecule leads to 2 products, right? It would be reverse. But let's focus on this. Oh boy, did I lose a number? So I divided by 2, that's this conversion here, times 373.71. Did you all get 6.27 grams of product? 6.27 grams of product. Okay. One of these are what's called the limiting reactant, and you're going to pick the reactant that gave you the less product. You know what? You know why that is? Because let's say you're chugging along, the reaction's chugging along, and you're making product, and you get up to 5 grams of product, then 5.4 grams of product, then 5.48 grams of product. At that point, one is done. If one is done, there's nothing left for Br2 to react with. So you don't get up to the 6.27 grams of product because one of your reactants has been consumed already. So you're picking the lower number. And you're saying that the limiting reactant, Lr, is 1. And that's important. That's important for what we're going to do next, which is the lab stoichiometry table. Okay. Yep. So this is the last part, and this is going to be new for, I think, almost everyone. Everyone has done, I imagine, in general chemistry, the limiting reactant or limiting reagent calculations. But it's a stoichiometry table that's pretty different from what you've done in the past, especially in general chemistry. Okay, stoichiometry table. Okay, the first thing is, I want to make sure I get this right. We could call it starting material, but you only want to use the compounds that are going into your product. You really want to use the compounds that you use to figure out the limiting reagent. You notice that we had nothing to do with this chloroform. That's just a solvent. Okay, these are the main starting materials. So that sometimes is a little bit tricky, but we'll call this SM, starting material. That's the first column. And the first starting material we're going to deal with is 1. Okay. Uh, let me just write it down here because this also sometimes presents a problem. For the stoichiometry table, only put the, right now I'm just call it the main starting materials. Or you could say the reagents used in the limiting reactant calculations, which I want to see in the lab notebook, okay, not on a scratch sheet of paper. Okay, and thus, since we figured out the limiting reagent calculations and we use both of these compounds, both of those compounds have to be in the table, and only these 2 compounds. All right, what does that mean? Typically, that means, well, not typically, no solvents. No solvent. No catalyst. A catalyst is not considered in the limiting reactant or limiting reagent calculations because a catalyst works when there's very little amount of it. What else? No chemicals used for purification. That's not part of the limiting reactant calculations. Okay, so don't put that in your stoichiometry table. Okay. This is going to go a little bit fast, but make sure that you have this stoichiometry table as an example. The next thing is amount. And I'm going to, well, no, I won't abbreviate it. I'll put amount. Next column is millimole. And the last column is called equivalence. And this is the one that causes some problems at first. Okay. The amount. The amount is literally the amount you used. We used, 1.15 milliliters. But to get the moles, we need this in grams also. So for each reagent, I'm going to take up 2 lines. And how do I figure out grams from this? What do? We just multiplied by the density. 1.15 times 0.69. Is that right? 0.794. That's how many grams. And I do want to see that in the stoichiometry table. 0.794 and put units so it's not confusing for the grader. Okay. Millimole. All right. We could get moles. So I take that number that I just calculated, divided by the molecular weight, divided by 54.09, and I get that. Oops, do you see that? So it's typically a small number. Sometimes it's even smaller than this. So I want to convert it to millimole. This is moles. Millimole is times 1,000, and it will give me, at least to the, what is this, the tens place, 14.7 millimole. Okay, you could put mole if you want. It's just that you're gonna have a lot of zeros typically, and I would just suggest that you convert it to millimole. All right, we're gonna leave equivalence until we figure out what's going on with the BR2. So here's BR2, okay, and do the same thing. We have 1.72 milliliters, and to figure out the grams, we multiply by the density. 3.12. Okay, so that's grams, 5.37. Is that really grams? That's a lot. Okay, let's do it. 5.37 grams. Okay. It's a lot compared to the butane, the 2-butane, but it also has a larger molecular weight. So let's see what happens with the millimoles. So I have that number saved. I rounded it for the table, but let's keep this number, and we divide it by the molar mass, which is 159.81. Okay, so that is the moles, right, times 1,000. That's the millimoles, 33.58. Okay, so that does look reasonable, because remember how we should have two equivalents for every one butane. But it's not exactly, right? It's not exactly 2 to 1. In our inspection, it is 2 to 1. 2 molecules of this, 1 molecule of this. But in real life, there's almost always going to be a reagent that's in excess. And that happens to be the bromine, right? It's the one that gave us more product. Oh, we'll get back to the stoichiometry table in just a bit. Since we have this number already, you know where that goes? 5.48 grams right there. That's what we expect. and I do want to see that right there underneath the product. Okay. Okay. So here's the deal with equivalence. And let me give you the rule that should help you out. First of all, the limiting reactant is set to 1.00 equivalents. Okay. It's like parts. Like if you're baking, you have 2 parts flour, 1 part water. But what is that part? It could be cups, it could be pints. It's just a ratio. So we're going to set this to 1 equivalent, the limiting reactant. Second is the one that you got to keep in mind. The equivalence is only based on the molar, sorry, not the molar. See, I made a mistake already. On the mole or the millimole amounts. Okay, don't worry about the ratio. Don't worry that it's a 1 to 2 to 1 ratio. We dealt with that already. We dealt with that when we figured out the limiting reactant. Okay, so only base it off of, and let's make it really simple. Since you figured out millimoles, just base it off the millimole amount. Okay, so while we have this fresh in our minds, the equivalence for the limiting reactant should always be set to 1.00 EQ. Even if it doesn't matter if this is bigger or smaller. We establish that this is the limiting reactant. Okay? If you establish that, this is automatic, right? This is automatic. Okay? And now you just want to take a ratio. What is X? Okay? So I'm not going to draw X here. I'm going to copy these numbers. 14.7 over 33.58 equals 1.00 over X. Figure out what X is. Do you see how I'm not worried now whether it's a 2 to 1 ratio? I'm not worried whether it's a 1 to 1 ratio. We dealt with that. Just look at the millimole amount. So it's just parts. And since this number is bigger, we should hope that this X is bigger than 1. We're going to cross multiply, then divide by 14.7. X equals 2.28 equivalents. That makes sense because in our reaction, it is a 1 to 2 ratio if everything is perfect. But remember how we said Br2 was an excess? Well, the excess is 0.28 excess. Put that number, 2.28 equivalents. That is the complete stoichiometry table. And this tells me right away that, sure, the chemical reaction I can tell is a 1 to 2 ratio, but to get our best results, the procedure wants me to use an excess of 0.28 equivalents. Okay, so again, I can't emphasize this enough because this is the most common mistake. The equivalence of 1.00 always goes with the limiting reagent. And then when you figure out the equivalence of the other reactant, you just do the ratio, right? Just do this. It's only based off the millimoles. All right. So really, for every reaction that you do, where you have to calculate an amount, a percent yield maybe, right? Right. This is your theoretical yield. You will need to most likely do the limiting reagent calculations and a stoichiometry table. And I know this video is long. I need to put one more thing. I need to put product. the two starting materials and the product. Because again, I want to know how much we make, and we've already figured that out, right? This is the theoretical amount, 5.48 grams. So 5.48 grams, and we could put here theo for theoretical. But what about the millimoles? Theoretically, it's this many millimoles because this was the limiting reactant. And for every one of the butane, we get one product. So theoretically, we have 14.7 millimoles of product as well. Okay. I'm not going to put in here equivalents, but you know it's a 1-to-1 ratio for the 2-butane and the product. I do want the last line to be the product. And go ahead and put a little note that this is not actual. This is what you're striving for. This is theoretical. Okay. And most likely you'll get less than this, but there's no reaction in purification that will give you exactly 100% yield